All right, thanks everyone for coming to my presentation, Side Channel Analysis for Cheapskates. So hopefully a few cheapskates in the room here that can enjoy why we want to attack hardware using very low-cost methods rather than the sort of typical high-end scopes that I'm also going to be showing. So I come from Halifax, Nova Scotia, Canada, which is the far east side of Canada, and it's actually somewhat easier between the friendlier EU customs and the flights for me to get here than it is to get to Las Vegas or California. So in between the next hour, between now and lunch, I'm going to introduce you a bit to what is side channel analysis. A lot of people have this rough idea of what it is, but it seems sort of magic. You have some device, you do something, and somehow you get the key. There's something in between those two steps, and that's this side channel analysis. The rest of the presentation is introducing a lot of these tools that I'm trying to help create and release. So there's some software I call Chip Whisperer, and that interfaces to some different waveform acquisition hardware, some different example systems that you can attack to learn about it, as well as sort of building your own amplifiers, building some of your own front-end equipment. And a quick, sort of very brief, where do you go from here? So it's important first to sort of define what the motivation of this talk is and what you can hope to get out of it. I'm not trying to create something that's just a simple script, that you can just run and it just works and does everything. This is all about learning about side channel analysis. So you're really going to have to spend time learning the underlying theory, learning some of the math. There's not that much math, to be honest. Learning how the algorithms are really working. It's not just okay, you connect this up, you hit this button, and poof, it works magically. So you will have to know something about hardware design, software programming, so both the embedded targets and the software running on the computer. And you're probably going to get frustrated. All the tools I'm sort of working on now, they do work, but they're ultra beta, alpha type tools. And you might have to contribute them a bit. It's all open source, as I said. And sort of tear into the internals. All right, so with that sort of disclaimer about what you might get out of this presentation, let's talk about the side channel, the power channel in particular. So we have a chip, and we have a main channel that you talk to it with, if it's the smart card, your communication channel, or any other comm channel. But there's something else here. The device also takes power, and this is where we get this power side channel. So over this additional channel, over this other information, we're going to learn something about the secret in the device. So using the main channel, you're not supposed to be able to learn anything about the secret. That's the whole point. But using this side channel, in this case power, we can. So how does this work? How does this sort of magic power channel work? Imagine you had some chip, Crypto Pro 9000, the latest digital logic chip. Inside it, it has a 4-bit bus, and there's 2 blocks. In this case, you can imagine between, say, the RAM and an ALU. Maybe it's just doing an algorithm in software, so it has to take data from RAM, move it to the ALU, does something on it, pushes it back. Those data buses are basically just small, very small wires that are sending data between them. You might think of it as something like this. So in this schematic here, if you're not too familiar with electronics, these are basically just switches. And they're switching the data bus line from either the VCC, so the positive, or the ground. So it can send a 0 or 1 by switching this bus line to one of those states. Now, this bus, which is effectively a long wire, relatively, I'm calling it, has a bit of capacitance. To change the state of a capacitor, it takes charge, which means it takes power. So every time we send a 1 or a 0, it takes a tiny, tiny, tiny amount of power from one of those, either the VCC or the ground rail. So what you can see is, imagine if I have 2 bits on a data bus, and with digital logic systems, there's always this clock. So everything is synchronized to this clock. On this clock edge, everything happens. At the next clock edge and the next time step, everything else happens. So we can imagine that if the data bus is first at the 0 state, and I want to move it to the 1 state, at that clock edge, it's going to take a tiny bit of power to do that. It's just physically required to change the charge on the bus. It takes this power. So if we looked at the power sort of in an ideal manner, what you would see is on each clock edge, you would see some spikes, either in the VCC rail or the ground rail, depending what the state is. So this very basic observation is sort of everything you need to know about power analysis. This is the root of why it works, is that it physically takes power to change the state of a normal data bus. And based on this, we can sort of break everything else, which I'll explain next. So there's two power models I should explain first you might hear people talk about. One of them is called Hamming distance, which is to say, on every clock cycle, the bus is going to change from one state to the next. So what I've shown here is what we call Hamming distance. So from here to here, where it goes from 0 to 1, it's taking this positive spike, and when it's going from 1 to 0, it takes a spike of the opposite direction. But these small microcontrollers I'm going to be showing actually have what we call a Hamming weight power model, which is to say that on every clock cycle, this isn't actually accurate. What it actually looks like is these spikes are just related to the current state of the data bus. So if there's a bunch of ones in the bus, there's always a positive spike, even if it's staying the same. Where this comes from is the buses do something called a precharge, which is, you can imagine if the data bus switches from all ones to all zeros, this would be the worst case power consumption. This would be require the most charge. Your worst case is going to limit your device in terms of speed and things like that. They can go over the data bus. So what they do is in between these two states, it's pre-charging it to halfway. So it's always putting it to this half state. To go from this half state to either positive or negative is going to take half the energy. So now when we go from all ones to all zeros, it's actually going to this half state in between and then goes to all zeros. An artifact is this, that every clock cycle, we can learn about the number of ones that is on the data bus, which is what we call the Hamming weight model. So the Hamming weight model is just saying that we always know the number of ones on the data bus. The Hamming distance is saying we know how many lines are changing on every clock cycle. So this seems like so far a very, very basic piece of information. We know just the number of ones on a bus. And how we use this, though, is that any sort of crypto algorithm, you put in stuff at A, comes out at B, and you can't find the secret key. But there's all sorts of intermediate operations, and this is what we target, this stuff here at C. So we want to learn information about these intermediate, supposedly secret operations, and if we learn that, then we can derive the secret key. So let me give you a very basic example of how this might work. Say I had a 4-bit system again, and say all it's doing is XORing data. I can put in any plain text I want, any single 4-bit number here, and there's a key. I don't know what the key is, and I also cannot look at the output, otherwise I could obviously very easily get this. So I somehow, knowing just what I put in and assuming I can measure the power, want to find out the key. So how we do this, first I'm going to talk about the original type of power analysis called differential power analysis, or DPA. So if you look up sort of the original paper in this field, this is what they describe. And then I'll talk about a slightly more advanced one that will be demoed here. So the original DPA attack, you put in this case, I have 7 input plaintext. I've just randomly chosen 7. It doesn't matter what they are. And I've measured the power while I've put those in. So now I have 7 power traces, and I can see, what was happening during that time. I can also guess what the hypothetical key might be. There's 16 possibilities that key could be. So I can take for each of those input plaintext that I know, because I chose them randomly, I can say, well, if the key was 2, I'm going to try every guess. I'm going to say if the key was 2, if the key was 3, etc. The hypothetical result would be 6. I'm going to take a look at a single bit of that 4-bit bus and say, well, in this result, bit 0 was a 0. In this result, bit 0 was a 1, etc. And I'm going to do that again for all of the 16 possibilities that I think the key could be. What I'm going to do now is split up the power traces associated with each bit 0 and bit 1 state. So all the power traces associated with the bit 0 being 0, I think is 0 in the hypothetical case, I'm going to put to one side, and all of them with the bit where I think it was 1, I'm going to put to the other side. Remember, I don't know the key, I'm just guessing, so I'm going to have 16 different arrangements of these power traces. If I was right, what I'd expect to see is somewhere there's going to be a difference between those two sets. Because if I was right, at some point, that single bit is always 0, so it's taking less power. At another point, that single bit was always 1, if I was right. And when I compare sort of the average, or add up all of those sets I've made, I should see this difference like that. If I was wrong, and assuming you have a lot of traces, not just 7, it should just average out to 0.5, and the rest of the bits should also average out to 0.5. So this is how we sort of do the original differential power analysis. There's a more powerful version that is called correlation analysis or correlation power analysis. And rather than targeting a single bit, we look at, okay, what is the hypothetical result? In this case, what is the hypothetical Hamming weight? So all of the bits. And again, I do the same thing. I guess what the key is. I have no idea. Just take every 16 possible guess. And I look at this hypothetical Hamming weight and see if there's correlation with my power traces. In one of these 16 cases, I should see somewhere with good correlation. Correlation meaning there's just a linear relationship between this and the amount of power, which will be true if my hypothetical result was correct. If you start to think too much about this example, you'll realize it's quite poor and will start to fail. For example, that first case, any key with bit 0 cleared gives you bit 0. So you're going to have multiple keys that are successful. In real examples, we wouldn't be attacking something like the XOR. What you might look at is the S-box output of the AES. So in AES, for example, which looks something like this at the input, what I'm doing is I'm just attacking, I'm trying to guess this key here. I know the plain text because this is what I put in, and I just guess, if the key was 0, I know what the plain text is, I know what the output of the S-box would be, and this is where I'm attacking. And you just do that for every one of the 16 subkeys. So if you wanted sort of a simplified algorithm, it would look something like that. So we input many plain text, we measure the power, and for each of the possibilities of the keys, for each of those 16 bytes, we calculate the S-box output. We use the power model, so the Hamming weight or Hamming distance, to see, well, what should the power trace look like? Should we have more power, less power? And we measure the correlation between the two. Whichever of those 256 key guesses had the highest correlation, we say, well, that was it. That was probably correct. And again, there's the AES. So to sort of simplify getting into this a bit, I've created this software I call Chip Whisperer, and it's all open source GPL licensed, and you can get it from chipwhisperer.com. All these are referenced at the end of the slides as well. So there's the Git repository, as I say, all of the tools I'm showing you here, all of the hardware designs, PCB layouts are all online in that repository. There's a mailing list for discussion, and there's a wiki for documentation. And to avoid, looks something like that, just so that people don't all stare at their laptops while I'm talking. So as you can see, there's a number of, I'm starting to add descriptions of some of the various software and hardware that you can use here. Let's go back to this. There's two main software packages, Chip Whisperer Capture. So this is my interface for capturing the power traces, and you can extend this to work with all sorts of other oscilloscopes if you want. And the Analyzer, which applies this attack I just described to the power traces. I'm using mostly Python for the GUI and the tools here, which not necessarily the fastest compared to straight C, but you can interface to a lot of other code from within Python. If you haven't used it, like MATLAB, you can interface to C code. And it's quite a bit easier for sort of getting into this if you want to make a few quick hacks. Python's very quick for that sort of work. So let me show you this. So this is the Chip Whisperer analyzer software. And let me sort of give you a preview of that. So if I run it, looks something like that. And I can load a capture that is included. The version of this on the CDs doesn't have sort of all these updates. There's a link at the end that has an updated zip that's exactly what you're seeing here. So example traces, this Chip Whisperer project. And we can look at, so these are power traces from a software AES implementation. It's a real AES library, and that I didn't write this. This is used by people in actual process. So we can zoom in, for example, on part of the computations, and you can see sort of some patterns in it. And you can plot, for example, a few power traces to overlay them, and you can start to see areas where they may differ a bit. For doing the actual power analysis, we can select, as I said, we had this type of attack, correlation, or the original DPA. We can select Hamming weight or Hamming distance type models and select how many traces. So remember when I said at the input, in that example, the DPA, I was putting in 7 traces. You may need a lot more traces depending on how good your capture is, what type of hardware you're attacking. In this case, I know I don't need very many. I'm only going to use about 40. And I hit attack. So it just takes a second to analyze it. So again, this is done with pre-captured traces that you have. So if you want to experiment a bit, you can easily do it without needing hardware or anything. So what this is showing at the bottom, oops. It's fairly slow to redraw. This is showing you for byte 0, this is the correlation between all possible key guesses. So it's plotting 256 possible key guesses. And in red, it's highlighted the one that I know to be correct ahead of time because I know what this key is initially. And what we can see is that the red trace at one point all of a sudden has much higher correlation. So this is telling you right at this point in time, this is where that operation actually occurred. So this is where the SBox lookup probably had occurred. And because it's software, you may actually see it happen a few times because perhaps this is a subroutine. The SBox is being looked up here from memory, and then later on it's passing that SBox output somewhere else, or it's passing it to one of the mixed column operations. So that's why you may see multiple. On the side here, there's a table. So this is just listing for each of the 16 bytes for the AES key. Let's see if I can pull this over. The screen resolution is a little limited here. So for each of the 16 key bytes, it's organized them by what is most likely the correct key and not. So we can actually see in the last case, because I cut this, I basically cut the trace down too short, this last key, it's failed to recover the correct key byte. The correct key is 3C, so it thinks it's 19, which is wrong, but all the rest of them are right. So it thinks it's 4F, which is right, CF, etc. So that's just a very simple correlation power analysis. And all down this column is the 256 possibilities that the key could be, again, organized by the highest correlation to the lowest. All right. So to do this, we obviously need to measure the power. We need to acquire those traces I talked about magically. So normally it might look something like this. This is using a hardware board called the Sasibo project, which is the standard evaluation board, and it's used in quite a few research papers. It has a resistive shunt, so you can measure the power across a resistor being used by the FPGA. And you just plug that into your scope. It has a trigger pin. So what this triggers doing, and I'm doing the same sort of hack here, is this trigger tells you specifically when about the AES is occurring. You might have noticed in that plot I had, I said, well, way over here in this window, this is where the actual operation is occurring. I had to acquire a whole bunch of points because I didn't know where the operation was going to occur. In real life, obviously, systems don't tell you, oh, this pin goes high right before I encrypt data. So you might have to use something like, when I send the last request to the device, I start a timer, and I know the AES will occur at some point between then and the result. So I'm just going to capture everything and run an attack over that. Once you know where in that space it actually occurs, you can sort of start to window it down to make your life a bit easier. And one question you might have, you might say, well, is that really typical? If you're in a university lab and you have a $20,000 oscilloscope, you're just going to use the $20,000 oscilloscope when you publish it. And when you look at a lot of work in this, it's always a fairly expensive scope. It depends a lot on the hardware device you're attacking. But critically, there are a number of papers showing that you do need this several gigasample per second rate to get good results when you're attacking hardware devices. There's just no way around it, is what sort of has been claimed before. And something like this might be shown where you have on the side what we call the partial guessing entropy. So this is how unsure you are of the result. When it goes to 0, you know perfectly what the result is. On the bottom, this is how many traces it's taken me to get this result. So if I only had to use 20 traces, I only need 20 measurements, so I just got 20 encryptions from the device, and I figured out the key. Obviously, the lower the better, because real devices are going to limit you to how many times you can, request the encryption, especially if you're getting it wrong, you're just sending in garbage. So this line here is with 500 megasample per second scope, and I'm attacking a very, very crappy target, so something that should work, without needing an expensive scope. When I go up to 100 megasamples per second, which is a fairly common sample rate for low-cost scopes, we can see we're now down out at about 80 traces required. As I go up, it just continues to get worse, so 50 megasamples per second. And when I'm down to 25 megasamples per second, it's working very, very slowly. It's going to take a long time to recover the key. But we can do better than that. We don't need those expensive scopes. And this is sort of the core part of my work, is showing how can we get rid of that one requirement for an expensive high-speed oscilloscope. And the problem is that when we measure the power, we really care about the power on the clock edge as it's switching. And we have the clock of the device often, if it's a digital system. So if you measure using this clock, so rather than using the oscilloscope's time base, you use this clock to define when the sample should occur, you'll see your results are much, much better. So this line here, this blue line, is measuring at about 7.4 megasamples per second. At 7.4 megasamples per second, stuff's very cheap. ADCs are very cheap to buy. If you have to buy a 500 megasample per second ADC, not even talking about buying a scope, just the physical chip, even that is expensive. So by using synchronous sampling, you can greatly reduce your cost requirements. And where this comes from, the sort of core part of this, is this requirement to synchronize your power traces. So these two graphs, the top one is sampling at 100 megasamples per second. This is sampling a hardware AES system that has basically doesn't work below about 250 megasamples per second. You need the minimum speed of the scope. In B, I'm sampling also at about that speed, 96 megasamples, but I've perfectly synchronized the clock to the device. In both cases, I have 10 traces overlaid. So in A, you can see that's garbage effectively. They're not lining up at all. In B, these 10 traces are perfectly lining up, and you can only barely see in a few spots where they differ. And again, exact same hardware, running 10 operations on the same data. Where this jitter sort of comes from is that the scope is always sampling. It has its own sample clock running all the time. When the device clock is going, it will start the encryption at some point, say this clock edge, but the scope is not going to be able to sample. It just cannot take a sample until later, when its own internal clock has gone high. But this isn't at all related to your device clock. So later, when you take another trace, and again, encryption starts here, it may have to wait a different distance before the next sample is taken. So now you have this sort of random jitter. The typical way they get around this is if you run this sample clock very fast, then this window becomes smaller. And that's the main reason the higher sample rate gives you such better results, is that it's sort of a hack to improve the synchronization. So a question might be, if you do have a normal scope that you want to use, what can you do? There's a few things. You can hack some of them to actually get at the sample clock, which, depending on how expensive your scope is, you may not want to do because it could damage it greatly. Many scopes will actually tell you, even though this happens, they can tell you what this time distance is with fairly high resolution. And you can do some tricks to upsample it, do a bit of shifting, and downsample it again. It's not going to be as good because you are losing information. By doing this, sampling at the wrong time, information is just gone. So you can try to do that. Or if you do have a high-speed scope, sample at the highest possible rate, and you can actually downsample if you want to have less data to deal with, but you'll help reduce this problem by sampling at the highest possible rate, even if you don't store at that rate. So to sort of make life easier, I've designed some open source hardware that can do this type of synchronous sampling, and this is just showing that it's basically achieving similar results. I'm using a 2 gigasample scope as reference, attacking this hardware platform, and it's achieving very similar results. So this global success rate is just saying, did I recover the key or not, averaged over a long time. So did I recover the key in 3,500 traces, averaged over a long time, and you can see they're crossing this 0.8 threshold, so 80% of the time I was right around the same point. So it schematically, or block diagram is something like that. You have a bit of an amplifier. You just have a high-speed ADC, a FIFO, and an interface to the computer. This type of board, if you have an FPGA board, you may actually be able to get away with what you already have. You may have an ADC on board the FPGA board that you can use. So what I've done is design this high-speed ADC board, and I'm showing it on this $80 AVNet FPGA board on the bottom here. Or there's a Ztex, a German firm that makes these other FPGA boards that have a slightly faster USB interface I also use. And I have both of those versions here if you want to sort of take a look at them. And I actually am trying to build an adapter board. Right now, you'll notice you have to do all this wiring yourself and add some voltage regulators. At some point, there'll be an open hardware adapter board that if you don't want to have to do all that wiring, but it's not up yet. As I say, if you already have an FPGA, depending how proficient you are, you might be able to just use it and get it working. A lot of research labs already have FPGA boards, so this is a great way to get into the very cheap side channel analysis. You just need some sort of analog front end, be it what I've designed or something else that you happen to have. Additionally, your scope might already have synchronous sampling. Some do. It's fairly rare. I know Clever Scope, for example, one of the USB oscilloscopes, has an option to add this external sample clock in. Some have an ability to synchronize to very specific frequencies, so you could sort of hack it together. And as I said, almost any other FPGA or ADC board will work. So say you were interested in doing this. One thing you might say is, well, I've seen people with these smart cards. I have one here, and they have these cool attacks, and they say, oh, I've attacked a smart card. I'm the greatest hacker in the world. And you can do that. So you can get a regular smart card reader like this, and all I've done is I've added this resistor in the power line here. You can't see it because it's a small surface mount resistor. And I've pulled out the clock signal. I've pulled out a synchronization signal. and I've pulled out the power measurement signal. So then the smart card reader looks something like that, with a little connector on the back. And I then connect this to the FPGA board so that I'm now measuring. I have the clock input and power is being measured there. And you can sort of run your attack algorithms. Now, if you're too cheap to buy a regular reader, you might be able to get away with building your own. So there's not a whole lot involved in it. This will only work with very specific smart cards. Again, all the schematics are online or in the white paper. And there's basically just a crystal oscillator here, and some additional connections to the I/O pins. But what you really have to understand with these smart cards in particular, and it's very specific to this, either they call them fun cards or ATmega cards, is this is a regular microcontroller. There's no difference between this and that DIP package microcontroller. It's a standard commodity microcontroller, so you're not really attacking a smart card with these. It happens to be in a smart card form factor, but that's the only sort of similarity it shares. If you can successfully attack that, that means nothing for attacking a regular smart card, which has some protection against these sort of attacks. So my suggestion, if you are interested in doing this, is to instead don't buy one of those smart cards because they can be a little trickier to find and expensive and you need that reader, is you just attack a AVR microcontroller like the type used in the Arduino. And you can either build up something on a breadboard like I have here, and we have a crystal, we have a shunt resistor under there, and I'm measuring the power across the shunt. I have the clock frequency coming out here, and I have a little USB to UART board to send and receive data, and also for power in this case. So, very simple. These might be parts you already have hanging around somewhere in a lab. What I have here, the same thing in a PCB version, so I've just built something that won't fall apart on me. Again, same, we have this microcontroller here, there's shunts under here, crystal oscillator, and the USB board. So that's just some of the parts. So again, I'm using this AVR, either Mega 8 or Mega 48 is the newer version. There is a note I should explain here. You'll see various versions of the microcontroller. The ATmega 8, ATmega 48P, 48A. One of the main differences is that Atmel has been using different production environments, which means different geometry on the actual silicon die. The A is the latest version and probably the only version you can now get from DigiKey or other distributors. And it has a slightly smaller power signature. In my testing, it doesn't really matter. They all work just the same. So I wouldn't really care about it. And I happen to use a specific USB to UART, but there's tons of manufacturers, SparkFun or whoever else makes these type of things. You do need the capture hardware. Here I'm showing this OpenADC board I've designed, but you can get away with general purpose scopes. If you're attacking this very simple board, you can probably get away with something like 100 megasample type I scope or similar. So you can do some testing then. The testing in this case, I send it some data, check the encrypted response is right. So this super simple board, all it does is you can send it a key, you send it a plain text, and it responds with the encrypted version. So that's all it does. Once you start looking into this, you'll have to say how noisy is it, how well is this going to work. So one of the first characterizations I do, or you should do with these boards, is I've connected the probe just to the power inline from the voltage regulator, or the voltage supply I'm using. What you don't want to see is this. You don't want to see a bunch of noise on it because that's going to give you trouble. So I've just, through trial and error, added some various filtering components until I've got this nice flat line. We then have this filtered power here. I add a shunt resistor there, and we're going to measure the power on the other side of it because this is a sort of solid reference, and we measure the power consumption there. You can sort of test if you send it the same data a bunch of times and you use a persistence mode in any scope, it doesn't have to be this, you should see the same results. So you should see this repeatable results. If you don't, then something else is wrong, be it the synchronization is bad, you have too much noise in the power supply, or noise is coming in somewhere else. And then you can just acquire a whole bunch of traces. Once you have them acquired, you can run that same attack program I showed you earlier and try to break it. So let me show you a capture example here. So everything's sort of real time, so there's always a good chance that it won't work. I apologize if it doesn't, but let's hope for the best. So this is the capture application. I select the type of oscilloscope I'm using, and I have this higher speed version connected. And I just connect to my simple serial device. So I can first check that it's working. So it just sends it some data, gets the response, and locally this program computates what it would expect the response to be and prints it. It doesn't actually check anything, it just prints it for you to look at. Here we have the trace. So it doesn't look like a whole lot yet. But let's see if we can get a little better here. Reset this. So what we can do is we can increase the gain in this spot here. So as I increase this, it's increasing the amplification in the front end. So this is auto scaling. You can see a little bit here. So these numbers are getting bigger. So we're starting to see some of this sort of repetitive nature that we had expected to see earlier. I'm finally going to switch to an external clock, and if it doesn't work, I just have to replug it here. So this is the part that is liable to fail. Let's try this. Restart. So as I say, because it's all real, there's always a good chance of this failure. But here it's working. So let me pull this back up for you. Oops. Increase the gain. And you can sort of start to see some signature there. So I'm going to set the trigger mode. So the trigger is what I said before. I have a pin that goes high right before the encryption happens. So I always want to synchronize to that rising edge. And I'll reduce how much data you have on screen here. So this is starting to look a little like what I showed before. So this is sort of a repetitive system. So we can see that as I'm sending different data, it's changing a little bit. And now all I'm going to do is capture a bunch of traces. So say I want 100 traces. And just hit Start Capture. Sometimes you have to try it a few times, or it crashes. The USB cables I brought have broken in my bag a bit, so it's giving me some issues here. So I'm just going to use the pre-captured ones for now. It does normally work pretty well. So this is what the physical hardware looks like that I'm just showing. We have the capture board here. So this is the analog board. The digital FPGA board's here. And this is the target system. As an alternative, so this was the other board I had showed. This is the LX9. So the FPGA part is this board. And the analog board is just plugging on top. If you come up after, when I have more time, I'll show you this running as well with the smart card. I don't want to waste time fixing that right now. So some other stuff you'll see when you look into literature is these magnetic field probes as well. Where you use these is that when you're attacking a system, I had inserted this shunt physically in the line. So physically, I put this resistor. I opened up the device, put this resistor right in there. You might not want to do that. It might not even be possible if it's a fairly recent device. So they use these magnetic field probes. Any current will create a magnetic field. You can use a small probe on the device to actually see the power it's using without even opening it possibly. But when you start to look at them and look at ones other people are using, you start seeing prices like $2,000, and it just doesn't seem very nice. But what you have to realize is that most of these probes are nothing more than something like a piece of semi-rigid cable looped around, soldered to itself with a bit of a slot to actually pick up the field. So you can do this for like $3 if you buy one of these cables off eBay. Nothing if you have a lab and you stole it from that lab or something. Either way, and this works quite well. I've sort of had some demos of showing this, and it achieves pretty much similar results to you'd expect. There's a few good papers of a guy actually, making a whole bunch of these. He's using them for a different purpose, but it's the exact same thing. And there's even someone who's done a thesis on how these magnetic field probes, making his own and testing them for different sort of characteristics. So there's a lot of great DIY references. And this is, again, a little cooler because you can do this without having to physically modify a real device. So when you're attacking something that isn't just a board you're making, you may want to use an EM probe instead. Part of this probe, you'll notice they have this preamplifier. And these preamplifiers are also very expensive. They tend to look suspiciously like some of these commercial ones that are only $90, but with a different label on them, and then $400 they're costing. So as you can guess, you can in fact just use these amplifiers instead. And they give you somewhere around this, the gain could vary from about 20 dB to 24 dB. But that's not cheap enough because you can just make one. You can get these ICs from DigiKey, which are about 60 cents in single unit quantity. And this is a gain of around 20 dB. And it just needs a 3.3 volt power supply, a few capacitors, DC block capacitors, and you can build something like that. So you remember that graph I showed before of this 20 dB gain? 20 dB is about 100 times, by the way, in a linear scale. So from 80 to 400 plus megahertz, I'm getting that sort of performance. At lower frequency, it gives you a little less gain, about 40 times gain. But either one of these or two of them chained together still works well enough for the cheapskate side channel stuff we're doing. It's far from perfect. Don't show these slides to an RF guy because they will not be impressed with me and this, particularly this one. There is also an open hardware PCB layout design too, so if you want something a little nicer. One other thing you're going to frequently see is a differential probe. So the theory behind this is that we have some common mode voltage, so some voltage is coming in here, and we're trying to measure the current across this resistor. Ohm's law is where all of this comes from. So for example, say we were trying to measure 0.2 milliamps. The shunt was 75 ohms. We'd expect about 15 millivolts across that resistor. The problem is that if you had 30 millivolts of noise, which isn't that much, you've basically totally obliterated your signal. And this common mode noise, for example, came from a regulator in the system I was using. So using a differential probe, the idea is that this common mode voltage will, to some degree, appear on both sides and be eliminated by looking differentially. I have to warn you, it's not quite perfect in this setup because the common mode voltage is not evenly applied to both sides. On one side, it goes through the resistor and is slightly reduced. But this type of differential probe still gives you a much, much better signal than just a straight connection alone. Although all the demos I have here are just straight connections. So looking at, this is a paper side channel analysis of AVR X Mega. And you might notice this guy's using a differential probe on this system. So again, the point is, say you are interested in this, you say, I want to do this, I want to duplicate these results. Well, what's that differential probe he's using? I want to get something similar. And you look it up on Mouser, and that probe, just the probe, is $4,500. So, that's not that cheap, but that's good up to 1,000 megahertz. So you can get a 200 megahertz version of it that's only $1,700. These are Canadian, so €1,000, something around there. It's still not that cheap. What about eBay used? Here's a used probe, and it's still $1,000 US. Again, this isn't good. This is not cheap. So how cheap are you? Again, you can buy an IC that does most of what you need, which is around $4.60, I believe, in single unit quantity. You need a few resistors and capacitors and supporting components, and hey, you get a pretty good differential probe. There's a layout for an actual circuit board as well as the schematic in the white paper online. So here's a few photos of some extra things that didn't quite fit in. If you start to look into this, you'll see a few different useful boards in this area. There's a company, Sakura, that makes the Sasibo G2 I showed earlier, the Sasibo W. This is not a cheapskate board, I warn you, though. It's like $1,500 or something. But you can use that ADC platform I was showing you earlier, plug it right onto the board. It has a reader for smart cards. It has quite a large FPGA for doing your own processing. So you can do some cool stuff, like say you wanted to do the attack in real time. You put the card in, you're doing the attack in hardware. This board is a good tool for that. Some of the targets that I don't have with me that you'll find reference to, the X Mega, so AVR X Mega is another microcontroller. This is interesting. It has a hardware AES engine, and in the previous paper I mentioned, this is actually what he's attacking. He's attacking the hardware AES, or I believe DES2 engine. You can even use an Arduino as a target. It is an AVR. It's almost the same AVR I'm showing here. And I've sort of hacked together a DIP socket with a resistor in one of the power lines. And then that resistor you connect up to your scope. So that's a sort of very low-cost type target. Another interesting thing that's not working right now, but at some point may, this is getting even cheaper. This is a X Mega, is another AVR microcontroller. This has a 2 megasample per second ADC built into it, as well as USB. So if you use this and can get it to synchronize properly with your target, you may be able to actually do an attack, not on a real device, I wouldn't say, but you can do an attack for learning purposes to test some of your own algorithms for $30 hardware, complete with everything. I also wanted to show you, so what can some of these power analysis results look like a little. So this is showing this AVR target running different software. And all 3 of these versions of software are in the Git or in the zip you can download. So there's what I call straightforward C, which is if you just wrote AES looking at the Wikipedia page or something, you'd end up with something like that. This is what most of the attacks I'm demoing are done with, is AVR CryptoLib, which is a fairly popular open source library for the AVR and similar microcontrollers. Written in C, which takes longer. And there's also an ASM version, so you can see the entire crypto is done long before. You can't really tell from this, but this is only the first few rounds of AES, whereas the ASM version is entirely done in that same time frame. So this gives you some sort of different attacks you can work with. If you're using the ASM one, for example, you'll find the attacks are not going to be as successful, or you need more traces because it's so condensed. And this is with the X Mega hardware I showed you. So there's, again, you can just compile that same library for it, or you can even use the hardware AES. With hardware AES, you notice it's done very quickly because it's all done in hardware. So I've sort of tried to ram through as much as I could, so you had an overview of everything I could think of. What do you do now if you really are interested in this? Well, the white paper for this conference has a lot more details of some of the stuff I glossed over. And this Chip Whisperer, chipwhisperer.com, also has a wiki with additional details. There's a mailing list, critically, so if you want to ask me questions, because not everything is on the wiki yet, send an email to that and I'll respond rather than just sending an email to me. And there's also a book called Power Analysis Attack, Revealing the Secrets of Smart Cards. And this goes over in a lot more detail all of the attacks and some of the countermeasures and a whole lot of stuff I just didn't remotely have time to cover. The original paper, DPA paper by Paul Kocher, is also quite interesting. I find a lot of people don't tend to go to the sources sometimes and read them. It's quite easy to read, so I highly recommend that. And there's a lot of interesting proceedings, too, if you want to sort of find out some of the more recent advances in this field. A hint, as a lot of these type of things may be behind paywalls, if you have any local university, they often have access to them, and you can just go to their library and read them from there. So I'll show a demo of the final, that thing working a game, but before I do that, are there questions or? Oh, yep.
Can you find chips with crypto processors to look at asymmetric crypto, or are those only real smart card chips still?
Okay, so the question was if there's chips that have asymmetric crypto to look at them. I don't actually know. I've only really focused on symmetric, to be honest. I know, for example, the X Mega only has symmetric cryptography in hardware. You may have to go to actual smart card devices to get that. I know Atmel makes a few security chips, so they're not smart card chips, but they're like small 3-pin devices that I believe, I'd have to check, yeah, it might be RSA. Some of them are harder to get, though. I know, like even not the smart card ones, but the small 3-pin devices, you need to have an NDA signed to even get the development kit, so that's not going to be useful. There is a number of Java cards you can buy. So these are real smart card targets, but they do have some support of asymmetric crypto, and you can sort of get started on them a lot easier. Other questions? No? All right. Well, thanks everyone for coming. Maybe if you want to go to lunch, you can leave now. Otherwise, I will try to get this demo working again here. So give me a few minutes, but it's up to you. All right, so this is what the capture looks like running. Oh, and it's done already. Oh, yeah. There's some issue with the USB. As I say, this cable I brought with me is very flaky, unfortunately. So you can see the number of traces going up quickly, and yeah, it crashes again. I may have to unplug the webcam.
What kind of cable is it?
USB mini, not micro, mini. Do you have one?
Yep.
Okay, excellent.
That one?
Yeah, one even closer. Thank you. Yeah.
This one. Kind of short.
Try this here. So we'll try another 100 traces. I can't show you it running. Hope it doesn't crash. No. Yeah, there's still some issue there with, I don't know. Anyway, assuming that worked, assuming, you would then run the that analyzer software I showed you. So I have a version of it there. So before I had loaded a new project here, I would just create a sample project somewhere. So save that somewhere. And I could import those traces that I had just run. Again, the BlackHat zip or CD actually has a version of just the capture, not the imported one. So you can test this without needing to have run that. So it will tell you how many traces you've done, run import. I can enable them and save the project. And I'm just going to reopen this. And open that project. So there is the traces again. You can see basically the same thing that was coming up on the screen before. And if you want to look, you can see how many traces sort of can overlay. And again, you can run that exact same analysis I showed you before. So in the exact same way, it's running that same sort of correlation power analysis program and trying to recover each of the key bytes in sequence. It gives you that same table I showed before and this sort of result output. So we can see the redrawing process is a little slow too. There we go. So again, we can see, because it's all the same hardware and same setup, we see the same type of trace I showed you before. Maybe it looks a tiny bit different. And we can zoom in and look at a few points that it was doing this operation on the S-Box. So that's a very brief overview to super cheap power analysis. Feel free to come up and I'll try to set up the other smart card reader I have here quickly. I think I'm well out of time for 2 minutes. It takes longer than 2 minutes. So thanks for coming, everyone. Hope you enjoyed the presentation.